Hey guys, Jake here, coming at you with some more math today. Here's what we're going to be going over today. Before we jump into this though, real quick, if you missed it, last week I did implicit differentiation week. This week we're going to be going over a bunch of limits as x approaches infinity or negative infinity. Here's what we're starting with today though, limits going to infinity and horizontal asymptotes in rational functions. So there's really a couple of different cases that when you're dealing with a rational function, that you'll come across, and I'm going to show you today how to deal with all those. So let's get into it. So before we get into limits with rational functions, let me just take a second to explain what a rational function is. So if you aren't already familiar with it, a rational function is essentially just a function that is a fraction where both the numerator and the denominator are polynomials. So here's what I mean by that. Essentially, we just have a fraction. We'll say both p of x and q of x, in this case, are both polynomials. Well, a polynomial is essentially just the sum or difference. These coefficients could be positive or negative of a bunch of constant times x to a whole number power. So essentially, you just have a list of terms. You may not have every single x power accounted for, but for example, a polynomial would be x to the fourth minus 3x squared plus x all over x cubed minus x plus 2. This is an example of a rational function because both the numerator and the denominator are both polynomials, right? We just have a bunch of terms being added or subtracted where each term could just be thought of as a constant coefficient times x to some whole number power, right? If we don't have a coefficient, you can imagine it's just 1, right? So just 1, -3, -1, 2, 1 would be our coefficients for all those, and then it's just being multiplied by x to some whole number, or just a constant in some cases. So these are an example of two polynomials. If you put them in a fraction over each other, that gives you a rational function. So this fraction here is a rational function. So when you're taking the limit of a rational function as x is going to infinity, there's really only a couple of different cases that you'll see, or I shouldn't say a couple cases, but any case you might see would fit into one of three categories. So this is the first category that I want to go over, where the degree, which essentially just means the power of the highest powered x on the numerator and the denominator, that would be considered the degree. So this is a fourth degree polynomial because the highest power x is 4, and this is a third degree polynomial because the highest power x is 3. So if the degree on the numerator is bigger than the degree on the denominator, like it is here, you'll see that the function as a whole, this entire rational function, the limit is either going to go to infinity or negative infinity. And let me show you how you know that. So what you want to do is think about dividing every single term by whatever the power of the highest x term on the denominator is. So what I mean by that is what we want to do is divide every single term within this whole thing by x cubed. So the reason why this works and the reason why this is okay is what we could think about is multiplying this entire fraction by 1 over x cubed over 1 over x cubed. Okay, so if we multiply by something over itself, this fraction here is just the same as multiplying by 1, right? Because anything divided by itself is just 1. So if we multiply something by 1, we're not changing its value. So therefore, doing this, distributing this 1 over x cubed into this entire fraction, both on the numerator and on the denominator, doesn't actually change its value. So if we do that, let's think about what will happen there. So 1 over x cubed times x to the fourth would give us x to the fourth over x to the third. 3x squared over x cubed, minus 3x squared over x cubed. Distributed in there, we would get plus x over x cubed. And this is all going to be over x cubed over x cubed minus x over x cubed plus 2 over x cubed. So now what we want to think about is simplifying each of these terms, right? So if we were to do that, we would think about each of these terms individually. So x to the fourth over x cubed would just be x. Don't forget our limit out front here. So this would just simplify to x. This would simplify, the x squared would cancel with 2 of these x's down here. So it would just leave us with minus 3 over x. This x would cancel with 1 of these x's down here, which would bring that down to an x squared. So we'd get plus 1 over x squared. Then here, x cubed over x cubed is just 1. X over x squared, that'll cancel. We'll just get 1 over x minus 1 over x. And then 2 over x cubed isn't going to be able to simplify. So now what this really all is going to come down to is one important fact, and that is that the limit as x goes to infinity of 1 over x is 0, right? If we have some constant, any constant would be fine. It would still give us the same thing. But some constant divided by some number that's getting infinitely big, this fraction is going to get really close to 0. And that's all this limit is saying, is as x gets bigger and bigger and bigger and bigger, if we have some constant that is not changing divided by a bigger and bigger and bigger and bigger number, our result is going to get closer and closer and closer to 0. Right? You could even try that plugging in values into a calculator. If you keep your numerator the same, keep it as a constant always, and start dividing it by bigger and bigger numbers, you'll see that your result is going to get really, really close to 0, which is all that limit is saying. So if we think back to our limit properties now, if we kind of think about what this is saying, if we apply those limit properties, essentially what that would be like is taking the limit as x goes to infinity of x minus the limit as x goes to infinity of 3 over x plus the limit as x goes to infinity of 1 over x squared all over the limit as x goes to infinity of 1 minus the limit as of 1 over x plus the limit of 2 over x cubed. So we're going to get like 6 individual little limits. Now, using this fact, this is true for higher powers of x also. So this would also be true for x squared, x cubed, x to the fourth, and so on. So all that's going to do is each of these terms, that is just a constant divided by a really, a number that's going to infinity, a constant divided by an infinitely large number, all these terms are all going to go to 0 as x goes to infinity. So as x gets really, really big, all these 4 terms here are all going to go to 0. And basically what happens is you're just left with the limit as x goes to infinity of x plus or minus a bunch of stuff that just goes to 0. So it doesn't really impact our limit anymore. And then it's going to be all divided by the limit as x goes to infinity of 1 plus or minus a bunch of other limits that all go to 0. So again, doesn't really impact anything. So all we're left with is this limit as x goes to infinity of x divided by this limit as x goes to infinity of 1. Well, the limit as x goes to anything of a constant is just going to be that constant. So basically, this is just going to be 1. So we're just going to get limit as x goes to infinity of x all over 1. Well, this is just going to be the same as the limit as x goes to infinity of x, which is infinity, right? As x gets really, really, really big, what number is x going to? Well, x would just go to infinity. It basically tells us there. So if the degree on the numerator is bigger than the degree on the denominator, the limit as x goes to infinity of this rational function is either going to be infinity or negative infinity if the coefficient of that term is negative. So you want to think about the sign if it's going to positive or negative infinity. But in general, it's either going to be infinity or negative infinity. So that's the first category. The next category is if the degree on the numerator and the denominator are the same. So this is the next category that we'll end up with, right? The degree on the top and the bottom is 2 in both cases because the highest power that x is being raised up to is 2. We can see that these are both polynomials because it's just some combination of some constant times x to some power being added or subtracted. If you only have one term, that's fine if it still falls into that category of a constant times x to some whole number power. So these are both still polynomials. They're being divided, therefore it's a rational function. The next thing we want to think about is basically dividing every single term by the highest power x in the denominator. So we could think about multiplying this by 1 over x squared over 1 over x squared. And what that's going to give us is each of these terms being divided by x squared, basically. So x squared over x squared plus 7 over x squared all over negative 3x squared over x squared. Okay? And then if we apply the limit properties, or I'm sorry, first we want to simplify. So x squared divided by x squared is just 1. 7 over x squared is not going to be able to simplify. And then negative 3x squared over x squared, the x squareds will cancel, we'll just have negative 3. Okay? So now you can think about the limit properties. If we apply those limit properties, this would be the same as the limit as x goes to infinity of 1 plus the limit as x goes to infinity of 7 over x squared all over the limit as x goes to infinity of negative 3. Okay, so now, just like we talked about before, this limit here, since we have a constant divided by x to some positive power, this is just going to go to 0. So that's not going to have any impact on our limit. So now all we really have is the limit as x goes to infinity of some constant divided by the limit as x goes to infinity of some other constant. So this is just going to give us this constant divided by this constant. 1 over negative 3, which is just negative 1/3. This second category, when your degree of the numerator is the same as the degree of the denominator, right? The highest powered x is the same on the top and bottom. As x goes to infinity, you're just going to end up with all the lowered powered x terms not really impacting anything. And then the biggest power x's kind of canceling out, and you're just going to be left with the coefficient of each, right? The coefficient here was 1. So we just ended up with 1 over negative 3, which is exactly what we had down here. So when the powers are the same, you just take the coefficients, and everything else pretty much has no impact, and you're just left with those coefficients, creating some sort of fraction. Okay, so this is the third category. We can see the degree of the bottom is bigger than the degree of the top because the highest powered x in our denominator is more than the highest powered x in our numerator. Okay, so it doesn't really matter the fact that we have this x being multiplied by some really tiny coefficient and this x being multiplied by, comparatively a much larger coefficient. It's still going to end up working out kind of similarly to what we've been having. If we multiply by 1 over x to the 5th times 1 over x to the 5th, or divided by 1 over x to the 5th, because, again, we're just going to multiply by 1 over the highest powered x that we have in our denominator. In our denominator, x to the 5th is our highest powered x, so we're going to do the top and bottom by 1 over x to the 5th. All that's going to end up giving us is 16x to the 4th over x to the 5th, 0.0001 x to the 5th over x to the 5th, plus 18x to the x over x to the 5th. So again, x to the 4th is going to cancel with 4 of those x's, and we'll just be left with 16 over x on our numerator. Our denominator, the x to the 5ths cancel. We just have 0.0001. This x will cancel with 1 of our x's on the bottom, and that term will just become 18 over x to the 4th. I'm sorry, we should have our limit out front here. So then again, just like before, this term and this term are both going to go to 0. Because as x gets infinitely big, some constant divided by an infinitely big number is going to get closer and closer to 0. So all we're going to be left with is 0 over the limit as x goes to infinity of this constant. Okay, so even though this x to the fifth was being multiplied by a really small coefficient, this still ended up being the only term that had any real value in the long term as x gets infinitely large. However, since the numerator of our fraction is going towards 0, 0 divided by any constant is just going to be 0. So basically, if the highest power x in our denominator is bigger than the highest power x in our denominator is going to get infinitely large much faster than our numerator is in the long term, and therefore we're going to end up with essentially the same kind of thing we had here, right? Where we have a constant, which in relation to our infinitely large x is pretty small, where our x is getting bigger and bigger. If our denominator is getting bigger and bigger and bigger faster than our numerator is, as x gets really, really big, that whole fraction is going to get really, really small. So that's exactly what's going on here. When the highest power in the bottom is bigger than the highest power in the top, the fraction as a whole is going to go to 0. That's all I have today. I'm going to be doing a bunch of more limit as x goes to infinity problems over the next few days for the rest of the week.